we're calling this example of the state of Massachusetts, just because I had a nice infographic for that. The population can be a statewide population, countrywide, subsets of it, as long as it is a well-defined population for which we can enumerate who is a part of it and what are the parameters involved in someone being a part of that population. And samples are randomly selected from that population and generally selected in more manageable chunks of some number of people for whom we can collect data on and do analyses on, because it is normally not practicable to study the entire population, except, for example, in a census. And remember, we've been using the Roman letters to describe sample data about the sample, and Greek letters to describe things about the population. And in general, inference is about taking data from a sample and inferring things about the population based on what we see in that sample. A little bit of vocabulary. The study units or the sampling units would be the individual elements of interest, often a person, but it could be something other than a person. It could be a school, it could be a neighborhood, but it is the smallest unit at which we are collecting data. The target population is the idealized population that we are trying to make inference about based on our sample. And the study population is who we are actually sampling from, which ideally would be the same as the target population, but if there are some individuals in the target population whom are excluded from sampling, then they may differ. And those kinds of systematic differences introduce selection bias. And finally, the sampling frame is just a list of all of the units in that study population, and this is required for random sampling. Oops. So again, we're using Greek letters for population parameters and the English alphabet for sample statistics. And I use the word statistic to mean that it's a description, something calculated from the sample, and a parameter for something that is calculated for the population. There are numerous strategies for sampling from the population. The one that we'll be concerning ourselves with in this class is the simple random sample. And this is the most straightforward to design and to analyze. There are good reasons to use other strategies, but this is your basic strategy where everyone in the population has an equal probability of being sampled, and it is random. So if there are 1,000 people in the population and you're selecting 10 people, then every individual has a 1% chance of being selected. It's the same for everyone. That's all there is to it. That's a simple random sample. Systematic sampling would be an approach where you have your records enumerated based somehow, and rather than randomly selecting from that, you take a systematic, for example, every record that is divisible by 3, something like this. Of course, if you're doing this, it depends on how your population is ordered, but there are certain cases where it makes sense, as I'll show with geographical samples. This approach can make sense. Stratified sampling is a way of improving or assuring the balance of certain elements of interest in your samples. So rather than giving everyone an equal an equal probability of being sampled, you can do things such as ensure a particular age representation in your sample by first taking a random sample of people who are from 20 to 29-year-olds, and then another sample of a given number in the 30 to 39-year-old range. So it is still a random sample, but you are drawing your random samples within strata so that you guarantee a particular representation of those strata. And this is a good way of reducing sample variation when you have strata that are important to your study. Cluster sampling is often a two-stage or multiple stage sampling process, and it is where you have where your individual records occur in clusters. So a classic example could be schools, where you have, say, 200 schools in the city, and then you have some number of students in each one of those schools. A cluster sampling strategy would be where you first randomly select some number of schools and then randomly sample the students within those schools. So rather than giving every student across the city an equal probability of being sampled, you're doing this in two steps, where you only select certain schools and then sample students within those schools. So a good reason to do that would be if you're studying an intervention at the school level where it has to be applied to an entire school or not applied. Or if it is simply not practical to go around to all 200 schools, you need to focus your efforts on some more limited number of schools. And this is something you will also be learning about later in your degree. And then there are so-called non-probability samples, where you are relying on volunteers, patients who come into a cancer clinic, or other kinds of convenient samples. These, of course, are prone to selection bias, in that the individuals who are willing to volunteer are systematically different than those who are not willing to, or they don't represent all of the target population. But in spite of that, they are often the only way to do studies. Well, we'll talk about this later. So I just wanted to give an example here in a geographical study. So here is a map where this area has been broken up into equal squares. And so these squares constitute our records. A simple random sample would be here, where every square has an equal probability of being sampled. And you see, some areas get less coverage, some areas get more coverage. So that may be, that it is a valid sampling strategy, but you do end up with a fair bit of sampling variation and a lot of coverage in some areas and not much in another. The systematic sample guarantees an equal representation throughout the entire area, and it is still a random sample if there is randomness involved in your starting point. So every block then has a known and non-zero probability of being sampled. The stratified random sample could be where, say, we define the area above this river here and the area below this river as separate regions, and we select a desired number of plots from each of those. So that way you eliminate the variability in the number of samples you get from each of these regions, although it's still a random sample. And here's one example of a non-probability sample where, I don't know, we're we're taking samples along some, either maybe this is a road where it's easy to get samples from, and a site here where for some reason we take samples. So what would you call the go viral study? Yeah, it's non-probability sampling. But I mean, in general, probability samplings and study like this are very expensive to do. So I imagine you would face the choice if you wanted to do a probability sample of New York, you would be paying 10 times as much to get the same sample size, or be getting a much smaller sample size to do the same thing. Some studies like the New York City Haynes, the National Haynes study are probability samples, and they're very expensive to do. So here is just an example of a population. This is the Run 10 data set, which is available as it's a common data set for statistical teaching, but it's all about 17,000 10-mile participants from this DC Blossom Run in 2009. So you could ask first, is this a sample or is it a population? Yeah, well, I guess it depends on how you're going to consider it. If your target population is the 2009 DC Cherry Run, then it's the population. And probably if you're doing analyses on some subset of that, you're going to be assuming that is your population. You could also think of it as a sample if really your interest was in all 10-mile runners or all the years of this competition, and you considered this to be somehow a representative sample of some larger number of runners. So these are running times, and the frequency in this population of 16,924. And if I take a random sample of 100 runners from that, you see that it pretty closely resembles the population. It's not exactly the same, but the shape of it is the same. The center is around 100 minutes, and it has the same bell kind of curve. So the individuals in this population, because I have randomly selected it in this example, are more or less representative of all of the runners in this big race. What is a sampling distribution? So what I just showed you, it was the distribution of individuals in a sample. That is not a sampling distribution. The sampling distribution is the distribution of something calculated from a sample like that, observed then over many samples. So an example of how you might generate a sampling distribution would be to take a sample like that 100 runners that we saw, calculate a sample statistic from it, let's say the mean, and then repeat that over and over. This is a frequentist definition of a sampling distribution. It's generated over large numbers of samples. And then the distribution of those means over many, many samples, that is the sampling distribution. So if you take a moment to think about that, in our study, or any study where you collect just one sample, which is what we usually do, one sample or two samples in a study, you are not observing the sampling distribution. You're only getting one observation from that sampling distribution. So this is an important thing to keep straight in your mind. There is a population distribution, and remember that the individuals in this sample more or less mimic the population distribution. This is not the sampling distribution. We're going to learn more about the sampling distribution today, but it is something that you will never directly observe unless you're doing a simulation on a computer. And these sampling distributions are different. Here's an example of a normal population distribution. So with a mean, this is serum cholesterol with a mean of 211 milligrams per 100 ml of blood, and a standard deviation of, I don't know, about what is this, 6 or 7, something like that. This is the distribution of serum cholesterol levels in the population. If we take samples, so a group of people, take the average of those samples over and over, the sampling distribution is going to look different. It's going to be more pointy, like this, so a narrower distribution. That's the key point. And this makes sense, right? Because you kind of expect that the average property of groups is going to be less variable than individuals. You know, if we look at the average characteristics of entire classes, they're going to be less variable than the individuals in those classes. So going back to this example of the 16,000 runners, where with a median of 33, mean of 36, standard deviation of 10, and then looking at the 100 runners, and I've already given this away to you, but is this an approximation of the population distribution or the sampling distribution? This is a sample of 100 runners. Sampling, yeah. Or wait a minute. Is this an approximation? Does this look like the population distribution, or does this look like a sampling distribution? It looks like the population distribution. It's got the same peak here at about 30, has about the same spread between about 20 and 70. We have a little less up here just because there are fewer extremes in the small sample, but it looks a lot like the population distribution.
Take 100 samples of them.
That's right. If we were to calculate the mean of this and then take 100 samples of that, that would be a sampling distribution. So this, even though this is from a sample, this is not a sampling distribution. Yes?
Usually when you look at the labels, if it says mean of something, that would be a sampling distribution.
Well, I wrote the mean here. This is mean equals 35.
Right.
It has a mean.
Right, but I said like the reason why this cannot be a sampling distribution is because the x-axis is runner age.
Instead of mean age.
Exactly.
Runner mean age. Yep, that is a way you could tell that it is not a sampling distribution. Also, just from my description, this is 100 runners. This is not, you know, the means of 100 samples, something like that. Everyone clear on that? Why this histogram is not a sampling distribution? Okay. So yeah, this mean of 35 would just be 1 point on the sampling distribution because it's a